There is a boundary surrounding us that we cannot see, cannot touch, and cannot cross. It does not exist on any map. No spacecraft has ever approached it. No telescope has ever photographed it. And yet, every astronomer on Earth knows exactly where it is, and exactly why reaching it is something humanity will never accomplish. No matter how far our technology advances, no matter how many centuries pass, no matter how boldly we choose to explore, it is not a wall. It is not a barrier in any physical sense. It is something far stranger, a horizon built not from matter or energy, but from the very nature of time itself. We call it the edge of the observable universe, and the journey to reach it, if such a journey were somehow possible, would be unlike anything the human mind was ever designed to comprehend. Tonight, we are going to make that journey. We are going to travel from where you are sitting right now, outward through the solar system, outward through the galaxy, outward through clusters of galaxies, outward through structures so vast they dwarf everything we have ever named, and finally, outward to the very limit of what can be known, the place where the universe, as we understand it, simply ends. Not because space ends, but because light itself runs out of time to reach us. Along the way, you will encounter distances that will quietly rearrange something in the way you think about existence. You will encounter timescales that make the entire history of human civilization look like a single footstep at the beginning of a journey measured in continents. You will encounter objects so strange and so extreme that the language we use to describe them feels almost embarrassingly inadequate. But before we leave, there is something you need to understand, something that changes everything. Most people, when they look up at a clear night sky, feel small. That feeling is natural. That feeling is appropriate. But the feeling of smallness that comes from looking at the stars with your naked eye is, in a remarkable way, almost comforting compared to what comes next. Because those stars, the ones you can see, the ones ancient civilizations named and navigated by and wrote poetry about, are your neighbors. In cosmic terms, they are practically next door. The farthest star visible to the unaided human eye sits roughly 16,000 light years away. That number sounds enormous, and in any unit of measurement we use in everyday life, it is. But placed against the true scale of what we are about to explore, 16,000 light years is a rounding error. It is less than a breath. It is the first step of a journey measured in billions of steps. And even then, we will not have arrived. This is why the journey to the edge of the observable universe is not merely a physical journey. It is a journey through the limits of human intuition. Every few minutes, the ground shifts beneath our understanding. Every few miles, in the cosmic sense of miles, the numbers we are dealing with require us to rebuild, from scratch, our sense of what large actually means. That process of rebuilding is not frightening. It is something rarer. It is perspective. And perspective, once gained, is one of the few things that cannot be taken away. So let us begin. The first thing to understand is that we are not starting from nothing. We begin on a planet orbiting a middle-aged star in one of the outer arms of a spiral galaxy that formed roughly 10 billion years ago. From where you are right now, you are already embedded in a structure of extraordinary complexity. The atmosphere above you stretches a few hundred kilometers before dissolving into the vacuum. The ground below you extends a few thousand kilometers to the planet's core. In every direction, you are surrounded by physical systems of remarkable elegance. weather, geology, magnetism, biology, all operating simultaneously, all interconnected in ways that took scientists centuries to begin mapping. And all of it, every last gram of it, is made from atoms forged inside dying stars. That detail is not a metaphor. It is literally true. The calcium in your bones was manufactured in the nuclear furnace of a star that exploded billions of years before the sun existed. The iron in your blood was produced in the final catastrophic moments of a stellar death so violent it briefly outshone the entire galaxy containing it. You are, in the most chemically precise sense possible, a collection of recycled stardust that has learned to observe the universe from which it came. That is where we begin. Now we leave, moving outward from Earth. The first thing that strikes you, even in imagination, is how quickly emptiness arrives. The moon is roughly 400,000 kilometers away, which sounds far until you realize that the distance from the Earth to the sun is approximately 400 times greater than that. The sun, our closest star, the source of every calorie of energy that has ever powered life on this planet, sits roughly 150 million kilometers away. A number so large that light, traveling at nearly 300,000 kilometers per second, takes 8 minutes to cover it. 8 minutes. That is how far away our nearest star is. Hold that number in your mind, because things are about to get considerably more extreme. Beyond the sun, the 8 planets of our solar system trace their orbits across distances that stretch the nearest thing to comprehension we can manage. Saturn, which from Earth appears as a point of light, a pale cream-colored dot that even a modest backyard telescope resolves into something breathtaking, orbits at nearly 10 times the Earth-Sun distance. Neptune, the outermost planet, sits roughly 30 times that distance. If the Earth's orbit around the Sun were the size of a dinner plate, Neptune's orbit would be the size of a small room. But the planets are not the edge of the solar system, not even close. Beyond Neptune, the solar system continues in a different form. A vast region of icy debris, frozen remnants from the formation of the planets, orbiting in an enormous cloud that surrounds the Sun at distances that are, even for astronomy, startling. This region, known as the Oort cloud, is thought to extend outward to perhaps 100,000 times the Earth-Sun distance, roughly 2 light-years from the Sun. 2 light-years. That is how large our solar system actually is, if you count everything gravitationally bound to our star. And yet, 2 light-years is barely the beginning, because our nearest stellar neighbor, the Alpha Centauri system, sits 4¼ light-years away, which means that even at the outer edges of the Oort cloud, we are not halfway to the next star. The space between solar systems is not merely empty. It is staggeringly, almost offensively empty. It is a silence so vast and so complete that calling it silence seems inadequate. This is the first lesson of the journey. The universe is mostly nothing. The matter in it, the stars, the planets, the nebulae, the galaxies, occupies a vanishingly small fraction of the total volume. If you compressed all the matter in the observable universe into a single point, and then let the universe expand back to its current size, you would recreate something almost indistinguishable from what we have now. Mostly void, with islands of complexity scattered across it, like cities seen from orbit at night. Small lights, enormous darkness. We have barely left the solar system, and already the numbers require recalibration. But what comes next requires something more fundamental. It requires letting go of the idea that distances can be felt the way we feel distances in everyday life. From this point forward, we will be working in a currency that is itself almost incomprehensible: the light year. The distance light travels in 1 year, roughly 10 trillion kilometers, a number so large that if you wrote it out in full, it would take most of a line of text just to write the zeros. Our galaxy, the Milky Way, is approximately 100,000 light years across. 100,000 years of travel at the speed of light. And light is not slow. Light crosses the diameter of the Earth in roughly 1/13 of a second. It travels from the Earth to the Moon in just over 1 second. It covers the Earth-Sun distance in 8 minutes. And yet, to cross our galaxy from one side to the other, even lighter would need 100,000 years. If you had been traveling at the speed of light since the moment modern humans first appeared on this planet, roughly 300,000 years ago, you would have completed about 3 crossings of the Milky Way. 3. The Milky Way contains somewhere between 200 billion and 400 billion stars. The uncertainty in that number is itself larger than most things the human mind can grasp. We are not sure if it is 200 billion or 400 billion, because counting stars in our own galaxy is surprisingly difficult. We are inside it, surrounded it by gas and dust that blocks our view in many directions, like trying to count the trees in a forest from somewhere in the middle of that forest. What we do know is that most of those stars have planets. Recent astronomical surveys have confirmed that planetary systems are not rare curiosities. They are the norm. Around most of the stars in our galaxy, worlds exist. Worlds with different sizes, different compositions, different temperatures, different histories. Some orbit in conditions that might permit liquid water. Some orbit in conditions of searing heat or absolute cold. And some, we do not know how many, but perhaps many, might orbit in conditions that could support life. We do not know. And that uncertainty is one of the most powerful unresolved questions in all of science. But that question is not what drives our journey tonight. Tonight, the question is simpler and in some ways more disorienting. How big is the universe? And the answer begins with understanding that our galaxy, the Milky Way, 100,000 light years across, home to hundreds of billions of stars, a structure so large that light itself takes 100 millennia to cross it, is not the universe. It is one galaxy, one of an estimated 2 trillion. The Milky Way does not exist in isolation. Nothing in the universe truly does. Gravity is a patient force, patient, constant, and universal. It operates across any distance, weakening with the square of separation, but never vanishing entirely. And gravity, operating across the billions of years since the universe began, has arranged the galaxies of the cosmos into structures, into groups, clusters, and superclusters, the way gravity arranged the debris of the early solar system into planets and moons. Our galaxy belongs to a gravitational family called the local group. The local group contains roughly 80 galaxies, ranging in size from the Milky Way and the Andromeda Galaxy. The 2 largest members, each containing hundreds of billions of stars, down to tiny dwarf galaxies with populations measured in millions rather than billion. The entire local group spans roughly 10 million light-years in diameter. 10 million light-years. The number requires a moment. Just a short while ago, in the terms of this journey, we were thinking about distances measured in light minutes. then light years. Now we are speaking of millions of light years, and we have not yet left our immediate cosmic neighborhood. The Andromeda Galaxy, our nearest large galactic neighbor, sits approximately 2.5 million light years away. The light you would see if you looked at Andromeda through a telescope tonight left that galaxy 2.5 million years ago. Before the earliest members of the genus Homo had yet appeared on Earth, you would be seeing a galaxy as it existed before human beings, in any recognizable form, walked this planet. That light has been traveling through the void since before our ancestors made the first stone tools. And it is just now arriving. There is something in that fact that resists full comprehension, no matter how many times it is approached. The universe does not send us news from other places. It sends us archaeology. Every photon that reaches our telescopes is a relic from the past. And the farther the source, the deeper into the past we are looking. This is not a limitation we can engineer our way around. It is not a problem that better telescopes will solve. It is a fundamental feature of reality. Light has a finite speed. The universe has a finite age. And together those two facts mean that looking outward across space is identical, in every physical sense, to looking backward through time. We are not seeing the universe as it is. We are seeing the universe as it was. And the farther out we look, the older the image becomes. Beyond the local group, the scale continues to expand in ways that simply refuse to become routine. The local group itself belongs to a larger structure, the Virgo supercluster, a vast collection of galaxy groups and clusters spanning approximately 500 million light years. 500 million light years. The light traveling across that structure when it began its journey was already old before multicellular life appeared on Earth. But even the Virgo supercluster is not the largest structure we know of. It is, instead, a component of something even grander, a structure discovered and mapped only in the past few decades, using increasingly sophisticated surveys of galaxy positions across the sky. This structure, called Laniakea, is a supercluster complex spanning approximately 500 million light years and containing the mass of roughly 100 quadrillion suns. 100 quadrillion. That is a 1 followed by 17 zeros. The total number of stars contained in all the galaxies within Laniakea exceeds any number that has a comfortable place in ordinary human experience. And Laniakea, enormous, ancient, barely comprehensible, is one supercluster among many. The observable universe contains roughly 10 million superclusters, 10 million structures, each the size of Laniakea or larger, each containing hundreds of thousands of galaxies, each of those galaxies containing hundreds of billions of stars. The arithmetic of the observable universe is, at some point, not a set of numbers but a feeling, a particular kind of vertigo that comes from standing at the top of a staircase and discovering that the staircase has no bottom. When astronomers began mapping the large-scale distribution of galaxies across the universe, constructing three-dimensional charts of where galaxies sit relative to one another across hundreds of millions of light years, they expected to find something roughly uniform, random, scattered. What they found instead changed cosmology forever. The galaxies are not scattered uniformly. They are arranged into a structure of breathtaking complexity and almost haunting beauty. A vast, three-dimensional web of filaments and sheets and voids that astronomers now call the cosmic web. Imagine a foam not a dense foam, but an extremely thin, fragile foam with enormous bubbles separated by paper-thin walls. Now imagine that the walls of those bubbles are made not of soap film, but of galaxies, arranged into sheets and filaments that trace the paths of ancient gravitational currents. And imagine the interiors of the bubbles as almost completely empty. Vast cosmic voids, hundreds of millions of light years across, containing almost nothing. This is the large-scale structure of the universe. The galaxies huddle along the filaments and at the nodes where filaments intersect, like dew along a spider web. The voids between them are, in many ways, the dominant feature of the cosmos. Most of the universe's volume is emptiness, punctuated by the thin lacework of matter that formed in the wake of ancient gravitational dynamics. What created this structure? The answer reaches back further than any star currently burning in the sky. It reaches back to the very beginning, or as close to the beginning as we can approach. The universe we inhabit today is approximately 13.8 billion years old. That number deserves its own quiet moment. 13.8 billion years. If you compressed the entire history of the universe into a single year, with the Big Bang at midnight on January 1st, and the present moment at midnight on the following December 31st, every event in recorded human history would fit within the last fraction of the last second of December 31st. The emergence of complex life on Earth would occupy only the final 2 weeks of December. The Sun itself would not form until early September, and the period we think of as ancient history, empires, written language, agriculture, would occur in the very last heartbeat of December 31st. We are newcomers to an old universe in the very earliest moments after the Big Bang, fractions of a second that exist at the boundary of what our current physics can describe. The universe was a state so extreme that the concepts of temperature, density, and energy lose their ordinary meaning. Temperatures trillions of degrees higher than the center of the Sun. Density beyond what any matter we know of could sustain. A universe not just hot, but almost inconceivably energetic, packed into a volume so small that comparisons to ordinary objects, marbles, grains of sand, atoms all collapse. Then it expanded. Not an explosion in the sense of something blowing outward into surrounding space. The universe did not expand into anything. Space itself expanded, carrying matter along with it, creating the volume of the cosmos, not from a center outward, but everywhere simultaneously. Every point in the universe moving away from every other point, not because objects are flying apart, but because the space between them is growing. This distinction matters enormously. It matters because it means the observable universe, the portion of the cosmos from which light has had time to reach us in 13.8 billion years, is not the whole universe. It is a bubble, a spherical region centered on our position, bounded not by walls, but by time. The light from objects beyond that boundary has not yet reached us, because the universe has not been old enough, for long enough, for that light to make the journey. And here is where things become genuinely strange. Because the universe is expanding, the size of the observable universe is not simply 13.8 billion light-years in radius. The distance light could travel in the age of the universe. It is larger, much larger. Because while light from a distant source was traveling toward us, the universe was expanding. The source that emitted that light was being carried away from us by the expansion of space, even as its light moved toward us. So, by the time that light arrives, the object that emitted it, is no longer where it appeared to be. It is much farther away, the edge of the observable universe, the surface from which the oldest light we can detect was emitted, sits roughly 46 billion light-years away in every direction, not 13.8 billion, 46 billion. A sphere of 46 billion light-years in radius, centered on Earth. Not because Earth is special, not because we are at the center of anything, but because an observer anywhere in the universe would see a similar bubble around themselves, centered on wherever they happen to be, defined by the same physics and the same speed of light and the same age of the universe. Every point in the cosmos is, in this sense, the center of its own observable universe. And no two of those bubbles are identical, because no two points in space have the same view. What lies beyond our bubble? Space continues, galaxies continue, the universe continues, but we cannot know, from observation alone, what is out there, because no information from those regions has yet had time to reach us. They are not invisible. They are not hidden behind a wall. They are simply too far away, in a universe too young for their light to have arrived. The edge of the observable universe is a horizon, and like all horizons, it moves as you move. If humanity could somehow travel to the very edge of our current observable universe, a new observable universe would surround that new position. The horizon would recede, the same physics would apply. The universe would still extend unknowably beyond. This is why reaching the edge is impossible in principle, not merely in practice. There is no edge to reach. There is only a boundary that is defined by where you are and how old the universe is. And both of those things change whenever you move. But there is something the horizon does not fully capture. Something discovered at the end of the 20th century that stunned the astronomers who found it and earned its discoverers a Nobel Prize. And that makes the terrifying quality of this journey something more than merely a matter of scale. The universe is not just expanding, it is accelerating. In 1998, two independent teams of astronomers studying the brightness of distant supernovae, stellar explosions whose peak luminosity can serve as a kind of cosmic measuring rod, discovered something that contradicted every expectation. The expansion of the universe was not slowing down. Gravity, acting over cosmological scales, was not reigning in the outward rush of galaxies from one another. Instead, something else was operating. Something pushing. Something causing the rate of expansion to increase over time. We call this something dark energy, because we do not know what it is. We have measured its effects. We can calculate its influence with remarkable precision. We know that it constitutes roughly 68% of the total energy content of the universe, and we know almost nothing about its fundamental nature. What dark energy means for our journey is this. The universe is not merely large. It is becoming larger, faster, every moment that passes. The galaxies beyond a certain distance are already moving away from us at speeds exceeding the speed of light. Not because they are moving through space faster than light, which is forbidden by relativity, but because the space between us and them is growing so quickly that the effective recession speed exceeds light speed. And those galaxies, the ones already receding faster than light, their light will never reach us. Not now, not in a billion years, not ever. They are, in a practical sense, already beyond our observable universe. We can see the light they emitted in the past, when they were closer, but any light they emit now is on a losing battle against the expansion and it will never complete the journey. The observable universe is not growing. In terms of what we will ever be able to see, it is shrinking. The acceleration of dark energy means that over time, the horizon retreats. Galaxies we can currently observe will, over billions of years, accelerate beyond the point where future astronomers could detect them. The cosmic web will thin. The local group of galaxies will eventually be the only structure gravitationally bound tightly enough to resist the expansion. Everything else will fade, redden, and vanish in the very far future, trillions of years from now. Any civilization that might exist in this universe will look out at the sky and see not 2 trillion galaxies, but only the merged remnant of our local group. The rest of the universe will have accelerated beyond detection. Future observers will have no way of knowing that there was ever a wider cosmos. The evidence will be gone. We are fortunate to exist at a time when it can still be seen. To travel to the edge of the observable universe is to travel backward in time. And the oldest light we can detect, the light that carries the most ancient information available to us, is not light from a distant galaxy. It is light from the universe itself. Roughly 380,000 years after the Big Bang, the universe had cooled sufficiently for electrons to combine with protons and form neutral hydrogen atoms. Before that moment, the universe was a plasma, a hot, opaque fog of charged particles so dense that light could not travel freely through it. Photons were constantly being absorbed and re-emitted, unable to move more than a short distance before bouncing off something. When the universe cooled enough for neutral atoms to form, the fog cleared. The light that had been trapped in the plasma was suddenly free. It streamed outward in every direction, filling the cosmos with radiation, and that radiation now stretched by 13.8 billion years of cosmic expansion into microwaves, rather than visible light, is still detectable today. We call it the cosmic microwave background. And it is everywhere. Not behind us, not at the edge, everywhere. Every direction you look. If you could see in microwaves, you would see this ancient afterglow, this ghost of the universe's infancy, this relic radiation from a time before any star had yet formed, before any galaxy had yet assembled, before any planet existed anywhere. It is the oldest picture of the universe we possess. A snapshot of the cosmos when it was less than 400,000 years old, seen through 13 billion years of travel. The temperature of the cosmic microwave background is almost perfectly uniform in every direction. A temperature of about 2.7 degrees above absolute zero. Almost perfectly uniform, but not perfectly. There are tiny fluctuations, temperature variations of roughly 1 part in 100,000, scattered across the sky in a pattern that has been mapped with extraordinary precision. Those fluctuations are the seeds of everything. The tiny density variations in the early universe, regions that were, by microscopic amounts, slightly denser than their surroundings, were the points around which gravity slowly gathered matter. Over hundreds of millions of years, those seeds grew. They attracted more matter. Halos of dark matter accumulated. Gas fell in. The first stars ignited. The first galaxies formed. The structure we see today, the cosmic web, the superclusters, the filaments, the voids, all of it traces back to those barely perceptible ripples in the cosmic microwave background. The distribution of galaxies across billions of light years encodes the physics of the first fraction of a second after the Big Bang. We can read the history of the universe in its structure, and we have barely scratched the surface of what that structure contains. There is something uncomfortable that must be said at this point in the journey. Everything described so far, the stars, the galaxies, the cosmic web, the ancient light, constitutes approximately 5% of the total content of the universe. 5%. The remaining 95% consists of two things we cannot directly detect, cannot fully explain, and do not, in any deep sense, understand. Roughly 27% is dark matter. Matter that interacts gravitationally, meaning it has mass and it curves space, and it pulls ordinary matter toward it. But it does not emit, absorb, or reflect light. It is, in a literal sense, invisible. It does not form stars. It does not form atoms in the way ordinary matter does. Whatever it is made of, it is something that does not participate in the electromagnetic force, which means it has no light. We know dark matter exists because of what it does. Galaxies rotate in ways that cannot be explained by the gravity of their visible mass alone. The stars in the outer regions of galaxies are moving too fast, as if they are under the gravitational influence of far more matter than we can see. The bending of light around massive galaxy clusters follows a pattern, consistent with enormous invisible halos of additional mass. The formation of the cosmic web itself required dark matter to serve as the gravitational scaffolding around which ordinary matter gathered. The universe as we know it, with its galaxies, its stars, its planets, could not exist without dark matter. It was dark matter's gravity that seeded the collapse of the first structures. Without it, there would be no cosmic web. There would be no galaxies. There would be nothing to look at when we look up. Dark matter is the invisible skeleton of the cosmos, and we do not know what it is. The most compelling hypotheses suggest it consists of particles that interact only through gravity and the weak nuclear force. Particles so rare in their interactions with ordinary matter that the roughly 100 billion trillion dark matter particles estimated to pass through your body every second leave no trace whatsoever. Other hypotheses invoke different physics entirely. The honest answer, after decades of searching, is that we have not yet detected dark matter directly. We have seen its shadow. We have mapped its influence. But the thing itself remains hidden. Dark energy, which makes up the remaining 68%, is in some ways even more mysterious. Unlike dark matter, it does not clump. It does not form structures. It is distributed uniformly through space, a property of the vacuum itself, and its effect is not to pull things together, but to push them apart, causing the accelerating expansion that will eventually carry the distant universe beyond any possible observation. What dark energy is, at a fundamental level, remains genuinely unknown. It may be a property of space itself, what physicists call a cosmological constant. It may be something more dynamic, changing over time. Distinguishing between these possibilities is one of the central challenges of 21st century cosmology, requiring observations of the most distant galaxies, accessible to our telescopes, and measurements of the expansion history of the universe with extraordinary precision. We are swimming in a universe we can mostly only infer. The portion of reality that we can see, touch, measure, and understand in any direct sense is a thin crust on the surface of something far deeper. And that deeper thing, whatever dark matter and dark energy ultimately are, shaped the universe we live in and will determine its ultimate fate. Let us go further back and further out. Between the era of the cosmic microwave background and the formation of the first galaxies lies a period of cosmic history known, with beautiful simplicity, as the Dark Ages. For hundreds of millions of years after the universe became transparent, there were no stars, no galaxies, no light sources of any kind. The universe was filled with hydrogen and helium gas, the raw material of everything that would follow, slowly being drawn together by gravity under the influence of dark matter's invisible scaffolding. Then, perhaps 200 to 400 million years after the Big Bang, the first stars ignited. They were nothing like the stars we are familiar with today. The first stars, sometimes called population 3 stars, to distinguish them from the later stellar generations enriched by heavier elements, formed from gas that contained only hydrogen and helium, the two simplest elements produced in the Big Bang itself. Without heavier elements like carbon and oxygen, the cooling processes that allow gas to fragment into smaller clumps were less efficient. As a result, the first stars are thought to have been enormous. Some estimates suggest masses tens or even hundreds of times greater than the Sun. And enormous stars burn fast. They lived for perhaps 1 million years, then died violently. Their deaths were not gentle. Stars that massive do not merely fade into white dwarfs or puff out into planetary nebulae. They collapse catastrophically, triggering supernova explosions of unprecedented power, and in some cases collapsing further into black holes. But in those deaths, they scattered the heavier elements they had forged in their nuclear furnaces across the surrounding gas. Carbon, oxygen, nitrogen, silicon, iron. The elements that would be incorporated into later stellar generations. The elements that would eventually find their way into planets, into oceans, into the chemistry of life. The first stars died so that everything else could live. Their deaths seeded the universe with the raw materials of complexity. The heavy elements enriched the gas clouds from which the next generation of stars formed. Those stars were smaller, lived longer, and in many cases formed surrounded by disks of gas and dust that coalesced into planetary systems. The universe became richer over time, more chemically complex, more structurally elaborate. The cosmic web grew denser at its nodes. Galaxies merged with each other, triggering bursts of star formation. Black holes at galactic centers grew by consuming infalling gas, sometimes releasing tremendous energy as quasars. Objects so luminous they outshine the entire galaxy around them, before settling into the more sedate supermassive black holes we find at the centers of most large galaxies today. In the centers of most large galaxies, including our own Milky Way, a supermassive black hole sits. Our own harbors a black hole with the mass of roughly 4 million suns. A giant by human standards, modest by the standards of the largest known black holes, which contain masses measured in billions of solar masses. The supermassive black hole at the center of the Milky Way is currently quiet. It is not actively consuming large amounts of material, but there are periods in galactic history when such black holes feed voraciously, heating the surrounding gas to temperatures that prevent star formation, shaping the growth and evolution of the host galaxy in ways astronomers are still working to understand. The galaxies we see today, complex, structured, varied, are the product of 13.8 billion years of mergers, star formation, chemical enrichment, feedback from supernovae and black holes, and the slow, patient work of gravity operating on dark matter scaffolding. established in the first fraction of a second of the universe's existence. Every galaxy is a history. Every star in every galaxy is a story. And we are, tonight, trying to reach the edge of all of it. Imagine, for a moment, that you could travel instantaneously to the boundary of the observable universe. Not to a wall, not to an edge in the sense of a cliff or a shore, to the region of space from which the cosmic microwave background was emitted. The surface of last scattering, as cosmologists call it, now located roughly 46 billion light-years from Earth in every direction. What would you see? The view would be astonishing in one direction and deeply unsettling in another. Looking inward, looking back toward the Milky Way, you would see, with some appropriately powerful instrument, a universe full of structure. Galaxies, clusters, filaments, voids, the same cosmic web, but from a different vantage point. You would see our galaxy as a faint smudge of light among billions of others, indistinguishable from the rest of the cosmic tapestry. But looking outward, looking away from us, toward the true edge of the observable universe, from your new position, you would see something different from what we see when we look in that direction from Earth. Because you are now 46 billion light-years from Earth, your observable universe extends 46 billion light-years in every direction from you. Which means you can see regions of the cosmos that are completely invisible to us. Not because we lack the technology, but because light from those regions has never had time to reach the Milky Way. The universe you would observe from that location would be similar to ours in its large-scale properties. The same physics, the same types of galaxies, the same cosmic web structure. Because the laws of nature appear to be the same everywhere we can test them. But the specific galaxies, the specific stars, the specific planetary systems would be entirely unknown to us. We have never seen them, and unless the universe's expansion slows dramatically, we never will. And if you then looked outward from your new position, past your own horizon, you would face the same situation again. Another vast region of the cosmos, invisible to you, visible to hypothetical observers in that more distant region. The universe does not end at any horizon. The horizons just change. This is, perhaps, the most disorienting thing about the edge of the observable universe. There is no edge, there is only limit, and limits, unlike walls, cannot be breached. They move with you, always maintaining the same relationship, always maintaining the same distance, always defined not by the properties of space, but by the properties of light and time. At this point in the journey, numbers have long since stopped being numbers in the ordinary sense. Let us try, one more time, to assemble a picture of the full scale of what we are discussing. The observable universe is a sphere, approximately 93 billion light-years in diameter. Within that sphere, there are an estimated 2 trillion galaxies. The average galaxy contains somewhere between 100 billion and 1 trillion stars. Most of those stars have planets. The observable universe therefore contains, at rough estimate, something on the order of 10 to the 24th power stars. A 1 followed by 24 zeros. More stars than grains of sand on all the beaches of Earth, by a factor of roughly 10,000. Around each of those stars, on average, several planets orbit, and we have so far confirmed, with certainty, only one place where life exists. Here, that number, 1, is not a verdict. It is not evidence that life is rare, or that Earth is unique in any cosmic sense. It is simply the current state of the search. We have been looking for confirmances of life beyond Earth for only a few decades, using instruments of increasing sensitivity across a universe whose smallest interesting regions contain more planets than there are people on Earth. The search has barely begun, but the question it poses, is there life elsewhere, is not merely a scientific question. It is a question that reaches into everything the journey tonight has stirred up. If the universe is this vast and life exists at all, the notion that it exists only here requires a very special kind of loneliness, a very improbable kind of rarity. A universe of 2 trillion galaxies, each with hundreds of billions of stars, producing exactly one inhabited world. That outcome would be as extraordinary as finding a single lit window in a city that stretches from horizon to horizon. It might be true. We do not know. But the scale of what we have traversed tonight suggests, at minimum, that the question deserves to be asked with seriousness, not with the assumption of company, but with genuine uncertainty, and with the understanding that an answer, when it comes, will be among the most significant discoveries in the history of our species. We have been speaking of the edge of the observable universe as a distance, 46 billion light years. But it is more accurate to think of it as a time. The edge of the observable universe is not a place we cannot reach, because it is too far away. It is a moment we cannot access, because it is too long ago. The surface of last scattering, the earliest epoch from which light can reach us, existed roughly 380,000 years after the Big Bang. Before that, the universe was opaque. No light from earlier periods could travel to us directly, because the plasma that filled the early universe absorbed photons once before they could escape. We have a wall, not in space, but in time, and it is not even the very beginning. Before 380,000 years, the universe existed. Events happened, physics operated, the conditions that seeded all the structure we observe were laid down in those early moments. But we cannot see them directly, because the light from that era was trapped, scattered, absorbed. We infer the earliest moments from the consequences we observe, from the ratios of light elements produced in Big Bang nucleosynthesis, from the fluctuations in the cosmic microwave background, from the large-scale structure of the cosmic web. We read the very early universe the way a detective reads a crime scene, not by being there, but by reasoning backward from the evidence left behind. What happened before the Big Bang? Here we arrive at the limit of what current physics can say with any confidence. Some cosmological models suggest the universe is cyclical, that Big Bangs are not singular beginnings but transitions, moments when a previous phase of the universe collapsed or transformed. Others propose that our universe is one of many, that the Big Bang was a local event in a vast, perhaps infinite multiverse, where new universes are constantly being created, each with potentially different physical laws. Still others suggest that the concept of before the Big Bang is not well defined, because time itself may have emerged along with space at the moment of the Big Bang, making the question of what came before as confused as asking what lies south of the South Pole. We do not know. And this is where honesty is essential. We do not know. Not in the sense of a gap in knowledge that will be filled next year or next decade. In the sense of a deep, genuine, unresolved question at the boundary of what our current physics can address. The edge of the observable universe is, in a way, the edge of the knowable universe. At least knowable in the direct observational sense. Beyond lies space we cannot see. Before it lies time we cannot directly observe. Around and within it lies a dark sector we can measure, but not identify. And yet, and this is the part that might be the most remarkable thing to emerge from tonight's journey, we know as much as we do. Consider for a moment the instruments. Not the mathematics, not the theories, the actual physical instruments that human beings have constructed, using materials found on a small rocky planet, orbiting an unremarkable star, to observe a universe 93 billion light-years across. The Hubble Space Telescope, launched in 1990 and serviced multiple times by astronauts traveling to low Earth orbit, observed galaxies so distant that their light left them. When the universe was less than 1 billion years old, a telescope the size of a large school bus, floating 400 miles above the surface of a planet, looking back through more than 12 billion years of cosmic history. Its successor, the James Webb Space Telescope, launched in December 2021 and stationed at a point 1 million miles from Earth, looks further still, with a mirror 6.5 meters across, folded for launch and unfolded in space, in a process that required hundreds of individual mechanisms to operate correctly, every single one. Webb can detect the infrared light of galaxies so distant and so redshifted that their ultraviolet starlight has been stretched by cosmic expansion into wavelengths far beyond what human eyes can see. Webb has observed galaxies that formed within the first few 100 million years of the universe's existence. It has detected starlight from an era so early in cosmic history that the universe was still in the process of reionizing. When the ultraviolet radiation from the first stars was burning away the neutral hydrogen fog left over from the dark ages, making the universe transparent to most wavelengths of light for the first time. These are not abstract achievements. They represent something genuinely astonishing about the situation we find ourselves in. That matter, organized into the particular configuration that produces a human brain, has found ways to look back across the full sweep of cosmic history and reconstruct what happened. We are the universe observing itself, not metaphorically, literally. The atoms in the telescope mirror are made of the same stuff as the stars it observes. The physics that governs the mirror's reflection is the same physics that governs the light, arriving from a galaxy 13 billion light-years away. There is no gap, no separation between observer and observed at the level of fundamental physics. We are continuous with the universe we study. That realization, when it lands fully, changes something. We cannot complete this journey without turning to face what lies ahead. Not for us, not for humanity in the span of any civilization we can meaningfully imagine, but for the universe itself. If the physics we currently understand holds across the incomprehensible timescales of cosmic evolution, the universe has a future, and that future is determined primarily by two things: gravity, which holds structures together, and dark energy, which drives everything apart. On the timescales we have been discussing, millions and billions of years, the story is one of continued expansion. Galaxies beyond the local group will continue to accelerate away from us, eventually crossing the cosmic horizon and vanishing forever from observation. The universe will thin. The night sky, already 99.9% dark, will grow darker still as the remaining visible galaxies recede. In 5 billion years or so, the sun will exhaust its hydrogen fuel and expand into a red giant, swallowing the inner planets and rendering Earth, if it still exists, uninhabitable. The Sun will then contract into a white dwarf, an Earth-sized remnant of compressed carbon and oxygen, slowly cooling over billions of years. Over trillions of years, star formation will slow and eventually cease as galaxies exhaust their supplies of star-forming gas. The stellar population will age, with the longest-lived red dwarf stars burning for tens of trillions of years before their fuel runs out. Eventually, the universe will consist primarily of stellar remnants, white dwarfs, neutron stars, and black holes. Cooling in an increasingly cold and empty cosmos, over even longer timescales, protons themselves may decay, if certain theoretical predictions prove correct, slowly dissolving the atoms that make up all ordinary matter. The white dwarfs and neutron stars will evaporate over periods so vast that writing them out requires scientific notation with dozens of zeros in the exponent. And the black holes? Black holes, according to a process predicted by the physicist Stephen Hawking in 1974, are not permanent. They slowly evaporate by emitting radiation, a quantum mechanical effect at the event horizon. Over timescales that dwarf even the lifetimes of the longest-lived stars, a stellar mass black hole would take approximately 10 to the 67th power years to evaporate completely. The supermassive black holes at galactic centers would take far longer, periods measured in 10 to the 100th power years or more. But eventually, even they would be gone. The universe, in the very far future, would be an expanding near void of thermal radiation, growing colder and more diffuse as space continues to stretch. No matter, no structure, no light sources, a state physicists call heat death. Not a burning death, but a cold one. The final equilibrium of a universe that has run down its energy gradients entirely. This is not a certainty. Our understanding of the very far future requires extrapolating physics we have tested across cosmological scales into regimes where we cannot be sure it applies. The behavior of dark energy may change over trillion-year timescales in ways we cannot currently predict. Quantum effects on cosmological scales may introduce phenomena we have not yet imagined, but based on what we currently know, the arc of the universe bends toward emptiness. And yet, and this is worth pausing on, we are here now in this specific moment of cosmic history, after 13.8 billion years of preparation. Supernovae that forged heavy elements, stars that spread those elements across space, molecular clouds that collapsed into solar systems, planets that developed chemistry complex enough to produce biology that evolved nervous systems capable of modeling the world around them, and eventually a species that looked up at the sky and began asking why. We exist at an extraordinary moment, not the beginning. The universe is already ancient by the time we appear, not the end. The universe will continue for incomprehensible stretches after any trace of us is gone, but a particular, remarkable, perhaps singular moment when the universe has produced something capable of understanding itself. That is not nothing. Throughout this journey, one question has moved quietly beneath the surface of everything. We have spoken of 2 trillion galaxies, of hundreds of billions of stars per galaxy, of planets around most of those stars, of chemistry that, on at least one world, produced living things capable of asking questions about the universe they inhabit. The mathematics of these numbers, combined with what we know about how life arose on Earth, makes it seem almost statistically implausible that ours is the only inhabited world in the observable universe. The numbers suggest company, The silence suggests otherwise. Astronomers call this the Fermi paradox, a name that honors the physicist Enrico Fermi, who, during a casual lunch conversation in 1950, asked a question that has not been satisfactorily answered in the decades since. If intelligent life is plausible in a universe this large, where is everyone? Why have we not detected signals, not received transmissions, not observed any of the engineering signatures we might expect from a civilization that has been developing technology for even a fraction of the time our universe has existed? The answers proposed over the decades are varied and, some of them, unsettling. Perhaps life is genuinely rare. Not improbable in the sense of 1 in a million, but improbable in the sense of 1 in a trillion. Perhaps the chemistry of life, which on Earth required nearly 4 billion years of evolution just to produce the first cells capable of complex behavior, depends on conditions and coincidences so specific that our planet is, against the backdrop of 2 trillion galaxies, essentially unique. Perhaps intelligent life is common, but communication is not. Distances so vast that signals dilute into indetectability, or civilizations so short-lived that they flash and vanish before their transmissions can cross the cosmic distances to another receiver. Perhaps there are signatures we have not recognized, or signals we are not equipped to detect, or forms of communication we have not yet conceived, or perhaps, and this is the answer that carries the most weight in quiet moments, the universe is not silent because it is empty, but because we have barely begun to listen. Our search for signals from other civilizations has been conducted, so far, over a fraction of the sky, across a fraction of the relevant frequencies, for a fraction of the time that would be needed for a comprehensive survey. We are, by analogy, a person who has spent a few minutes standing in a forest listening for birdsong, heard only wind, and concluded the forest may be empty of birds. The forest is enormous. We have not yet been quiet for long enough to know what lives within it. We are approaching the boundary now. Not physically, in understanding. The edge of the observable universe is, as we have established, a horizon, a limit imposed not by any property of space itself, but by the combination of the speed of light and the age of the universe. It is a temporal boundary masquerading as a spatial one. But there is something else worth considering: the nature of the information that travels across these distances. Every piece of knowledge we have about the universe beyond our planet has arrived via electromagnetic radiation. Visible light, radio waves, X-rays, gamma rays, infrared, ultraviolet. All of it is light, in the broad physical sense. Oscillating electric and magnetic fields propagating through space at 300,000 kilometers per second. That limit, the speed of light, is the fundamental constraint on how much of the universe we can know. Not observe with current technology. Not observe with any conceivable technology. Know in the sense of having received any information about at all. 2 developments in recent years have begun to add new channels of cosmic information, beyond light alone. The first is gravitational waves. Ripples in the fabric of space-time produced by the acceleration of massive objects. When 2 black holes spiral together and merge, or when 2 neutron stars collide, they send gravitational waves propagating outward at the speed of light. These waves can pass through ordinary matter without interacting with it, arriving at Earth, carrying information about their source that light cannot provide. The detection of gravitational waves in 2015 by the LIGO collaboration opened a new window on the universe. a new sense, in a way, through which the cosmos can be perceived. The second is neutrinos, fundamental particles produced in nuclear reactions, including those in the cores of massive stars and in supernova explosions. Neutrinos travel at nearly the speed of light and interact so weakly with ordinary matter that they pass through the entire Earth without scattering. Neutrino astronomy is still in its early stages, but it represents another channel through which the universe speaks in a language different from light. A future astronomy that combines electromagnetic observations, gravitational wave detection, and neutrino measurements will have a richer picture of the cosmos than any of these channels alone can provide. And yet, all of these messengers, light, gravitational waves, neutrinos, travel at or near the speed of light. None of them can carry information from beyond the cosmic horizon. None of them can tell us what lies outside the observable universe. That boundary is, for now and perhaps forever, absolute. We have traveled far tonight, further, in some sense, than any physical journey allows. We have moved from a planet circling an ordinary star, outward through the solar system, across the gulf between stars, across the breadth of a galaxy, beyond the galaxy into the local group, beyond the local group into superclusters and the cosmic web, outward to the limit of the light we can detect, and then further still in concept, to the structure of the universe itself, to the nature of its beginning and the trajectory of its end. What does that journey leave us with? Not answers exactly. The honest accounting of this journey includes a great deal of genuine uncertainty, a great deal of we do not know, and a great deal of acknowledgement that our current understanding, as far as it reaches, still falls short of the full picture. But uncertainty is not the same as ignorance. There is a difference between not knowing something and having no information about it. We have a great deal of information about the universe, more than any previous generation of humans, accumulated through centuries of painstaking observation, mathematical reasoning, and technological development. What that information tells us is something like this. The universe is ancient, old enough that most of the stars which will ever form have not yet been born, because star formation will continue for trillions of years. It is vast, vast enough that the light from the most distant observable regions has traveled for nearly the entire age of the universe to reach us. It is structured, not randomly, but in ways that reflect the physics of its origin, the dynamics of gravity, and the properties of dark matter and dark energy. It is chemically complex, full of the elements that give rise to planets, to oceans, to the molecular machinery of life. And it is, in at least one place, inhabited by creatures curious enough to ask what it is. The terrifying quality of the edge of the observable universe is not really terror in the usual sense. It is awe wearing terror's clothes. The scale is too large for comfort. The implications are too deep for easy assimilation. The uncertainties are too fundamental to be papered over with confidence. But awe, once you let it in, is not paralyzing. It is clarifying. Beyond the edge, beyond the 46 billion light-year radius of the observable universe, the universe continues, space continues, matter, in all likelihood, continues. The laws of physics, as far as we can reason about it, continue. But we will never know what is out there in any direct sense. We cannot send a probe, because no probe could ever travel fast enough to escape the expansion of space between here and there. We cannot send a signal and receive a reply, Because any reply would take longer to return than the current age of the universe, and the universe will have aged and changed dramatically in that time. We cannot receive any light from those regions, because the light from objects currently beyond the horizon has not yet had time to reach us. And due to the accelerating expansion, some of it never will. The beyond is truly beyond. And this permanent, principled, inescapable limitation on what we can know is perhaps the most profound boundary in all of science. Not a boundary that better instruments will eventually cross. Not a boundary that more funding or greater cleverness will overcome. A boundary written into the structure of the universe itself, arising from the combination of a finite speed of light and an accelerating expansion, producing a cosmic horizon that we inhabit but cannot escape. We are, in the most precise sense, islanded. The observable universe is our island. Beyond it, other islands exist. Other observable universes, centered on other points in space, separated from ours by regions we will never see. Each of those other islands, if inhabited, would have observers who face the same horizon we do. Each would have its own edge of the observable universe, beyond which lies yet more inaccessible cosmos. The universe may be infinite. The regions we can ever access, observe, or learn about constitute a finite bubble within that potential infinity. And the bubble is not expanding to include more. It is, due to dark energy, effectively shrinking over cosmological time in terms of what the future will be able to see. What exists beyond our horizon is, in the only operationally meaningful sense, unknowable. That is a hard thing to sit with. But there is another way to look at it. We live at an unusual moment in cosmic history. Not unusual in the sense of being at the center of something. We are not at the center of anything. But unusual in the sense of being at a moment when the universe is still young enough that the cosmic web is visible, still structured enough that individual galaxies can be resolved and studied, still close enough in time to its origin that the cosmic microwave background radiation is detectable. In the far future, say, 1 trillion years from now, an observer in whatever civilizations might exist at that time would face a very different sky. The galaxies beyond the local group, accelerating away due to dark energy, would have crossed the cosmic horizon and vanished. The universe visible to that future observer would consist essentially of the merged remnant of our local group, a single large elliptical galaxy surrounded by darkness. No other galaxies visible, no cosmic web to map, no evidence in the sky that the universe contains anything other than one enormous stellar system. That future civilization, if it existed and if it lacked access to records from earlier epochs, would have no way of knowing that there were once 2 trillion galaxies visible in the sky. It would look out at the darkness and, quite reasonably, conclude that its galaxy was the universe. It would have no way of knowing what we know. It would face a diminished cosmos, stripped of the richness that dark energy is slowly pulling beyond reach. We are living in the epoch when the universe is most knowable. The 2 trillion galaxies in the sky represent a treasure of information about cosmic history, about the physics of the early universe, about the nature of dark matter and dark energy. That is available now, that will become progressively less available as the universe ages and the distant galaxies accelerate beyond detection. If there is ever going to be a civilization in this universe that fully understands how the cosmos began and how it evolved, that civilization needs to exist in an epoch like this one, Possibly in this exact epoch, possibly now. That thought carries its own weight. Let us return. Not because the universe offers a way back. It does not. Once light leaves its source, there is no retrieval. Once a galaxy crosses the cosmic horizon, there is no recovery. The universe moves in one direction only. Forward through time, outward through expansion, deeper into complexity, and eventually into entropy. But we can return in the only way that matters, from where we began, in understanding. We started on a planet around one star, in one galaxy, in one cluster of galaxies, in one supercluster, in one corner of a cosmic web that spans the observable universe. A planet small enough that a human being can walk its circumference in roughly a year. A planet so small that from the orbit of Saturn, it appears as a pale blue dot, barely distinguishable from starlight. That planet, this planet, produced, in the ordinary course of chemistry and biology and evolution, beings capable of reconstructing the history of the universe they inhabit. Beings who, using nothing but light falling on mirrors and lenses and photosensitive detectors, have mapped the cosmic web, detected the echo of the Big Bang, measured the acceleration of universal expansion, observed the collision of black holes through ripples in space-time, and glimpsed galaxies that existed when the universe was less than 5% of its current age. That achievement, modest compared to the scale of what remains unknown, extraordinary compared to where we began, is worth pausing on as we complete this journey. We did not start with the answers. We started with fire and stone, with boats and star charts, with the unaided eye turned upward on clear nights, and the slow accumulation of pattern and meaning. The road from starting point to the James Webb Space Telescope took hundreds of thousands of years, and the contributions of countless individuals whose names are mostly lost to history. The universe did not hand us its secrets. We worked for them. We argued about them, corrected our mistakes, built on what came before, and pushed further. And what we found, at every step, was more complexity than expected, more structure than expected, more history than expected, more unknowns than expected. The universe, examined closely, does not become simpler. It becomes richer. Every answer opens new questions. Every instrument reveals phenomena that previous instruments could not detect. Every advance in understanding exposes the next layer of what we do not yet know. That pattern shows no sign of ending. We have been speaking of the edge of the observable universe as if it is a fixed thing. In one sense, it is. A sphere of 46 billion light-years radius, centered on our position in space, bounded by the physics of light and time and universal age. But in another sense, it is always changing. Every second that passes, the universe grows a second older. Light that was previously too distant, light that had not yet had enough time to reach us, arrives. The sphere of what we can in principle detect grows, slowly, as time advances, and new photons from the deep past complete their journeys to our position in space. We are, at every moment, receiving new information from the ancient universe. Not new in the sense of recent events. That information is from billions of years ago, but new in the sense of newly arrived. Light that has been traveling since the universe was young is arriving at Earth right now. It has been in transit for billions of years, crossing void and structure and more void, and it is arriving now. And that arriving light carries history. Every photon from a distant galaxy is a document. Every microwave from the cosmic background is an archive. Every gravitational wave from a black hole merger is a recording of an event that happened before the solar system existed. The edge of the observable universe is not just a boundary, it is a library, and we have barely begun to read it. The universe does not resolve neatly. A journey to its edge does not end with a destination. It ends with more horizon, more darkness beyond the horizon, more questions than answers, more unknown than known, more space than matter, more past than present, more uncertainty than certainty. And that is appropriate, because the universe is not a problem to be solved. It is a reality to be inhabited and, to whatever extent our instruments and our mathematics allow, understood. The edge of the observable universe is not the end of something. It is the current limit of our reach, and limits are not endings. They are the present frontier of an ongoing process that began when the first human looked up at the night sky and wondered. What we have established tonight is this: the observable universe stretches 46 billion light years in every direction from where you are sitting. It contains 2 trillion galaxies. It formed 13.8 billion years ago from an event of extraordinary density and heat. It is composed of 5% ordinary matter, 27% dark matter, and 68% dark energy, the last 2 of which we do not fundamentally understand. It is structured into a cosmic web of filaments and voids, shaped by the invisible scaffolding of dark matter and the ancient physics of the Big Bang. It is expanding, accelerating, and growing less knowable over cosmic time. It produced, in at least one location, chemistry capable of life, biology capable of curiosity, and curiosity capable of asking what this all is. And it will continue, long after every star currently burning has faded, long after every black hole has evaporated, long after any trace of the matter from which we are made has dispersed into the expanding void to exist, dark, cold, quiet, and immeasurable. The edge of the observable universe is not terrifying because it is dangerous. There is nothing at the edge that threatens us. It is terrifying because of what it implies. That the reality we inhabit is orders of magnitude larger than our intuitions were built to accommodate. That most of it is forever beyond our reach. And that even the portion we can access is mostly made of things we cannot see, governed at its largest scales by a force we cannot identify. We are small, we are brief, we are, as far as we know, rare, and we are here at this particular moment in the history of a universe that will not look like this for long, with the accumulated tools and knowledge of 10,000 years of human inquiry, looking outward at the full enormity of what exists. That is not nothing. That is, in any honest accounting, everything. The sky beyond your window tonight is the same sky it was before you began this journey. The stars are in the same positions. The moon, if it is visible, is in the same phase. The darkness between the stars is the same darkness. But it is not the same darkness it was before, because now you know that the darkness between the stars is not empty. It is full of structure invisible to the eye. Dark matter, dark energy, the thin filaments of the cosmic web, the photons of the cosmic microwave background carrying information from a time before any of those stars existed. The darkness is ancient, and it is active, and it extends in every direction from where you are, for 46 billion light years before it reaches a boundary that is not a wall but a horizon, beyond which the universe continues, unknown. For a distance that may have no limit, we will not reach the edge in our lifetimes. We will not reach it in any lifetime. It is not a place to be reached, but it can be understood, and understanding it, even partially, even provisionally, even knowing that the understanding will be revised as we learn more, is one of the most remarkable things that matter, in this particular configuration, has ever done. The universe made us curious enough to look. That is the thing worth carrying home.